Every neural network learns by answering one question over and over. If I nudge this one number, does the final error go up or down, and by how much? That single number, the sensitivity of the loss to a weight, is called its gradient. Computing that sensitivity for millions of weights sounds impossibly expensive, yet backpropagation does it in essentially one sweep across the network. Today we are going to see exactly how, by treating the network as a system of pipes and letting error flow backward through them. Let me set the ground rules for our metaphor. A forward pass is water flowing left to right, filling each node with a value. The backward pass is a different kind of signal flowing right to left, carrying blame for the final error back to every part that caused it. Before any of that, we need to see a computation as a graph, not a mysterious brain, just a chain of tiny operations. Each operation takes some inputs, does one simple thing, and passes its output onward. Here is the smallest example that still shows everything. We take an input, multiply by a weight, add a bias, squash it, do it again in a second layer, and finally compare to a target. 6 little steps, and Backprop will handle all of them the same way. Let's give it real numbers so nothing stays abstract. Our input is 2, the first weight is 3, and the first bias is 1. Watch the value flow forward and fill the first few nodes. 2 times 3 is 6. That is the multiply node lighting up. This is the forward pass beginning, and notice how each node simply waits for its inputs, then computes one thing. Now add the bias of 1. 6 plus 1 is 7. The pre-activation of layer 1 is 7, sitting in the next node, still glowing as the water moves rightward. Next comes the activation, the squash. For clarity, we will use a simple one that keeps positive numbers as they are and zeroes out negatives. 7 is positive, so it passes straight through as 7. That 7 is now the activation of layer 1, the input to layer 2. The forward pass has crossed the first layer completely. Let me carry the water into the second layer. The second weight is 1/2, and the second bias is 0. 7 times 1/2 is 3.5. Add 0, still 3.5. This is the pre-activation of layer 2. Pass 3.5 through the activation again. It is positive, so it survives unchanged. Our network's final prediction is 3.5. Finally, we compare to the target. Suppose the correct answer was 2. We measure error as half the squared difference, a standard choice that makes the algebra clean. 3.5 minus 2 is 1.5. 1.5 squared is 2.25. And half of that is about 1.13. That is our loss, the single number the whole network is judged on. The forward pass is complete, every node lit up left to right. Now the real question. How much is that loss the fault of the first weight, the 3 we chose? To find out, we do not restart, we send a signal backward, and this is where backpropagation earns its name. The backward signal at each node answers a local question. If my output changed by a tiny bit, how much would the loss change? We will carry this quantity, the sensitivity of the loss to a node's value, backward through the graph. At the loss itself, this is easy. The loss is half the squared difference, so its sensitivity to the prediction is just the difference, 1.5. That is the amount of blame flowing out of the loss node. Here is the single idea the entire algorithm rests on. As the error signal passes through each node, it gets multiplied by that node's local derivative, how much the node's output responds to its input. This is the chain rule in motion. Think of each node as a valve on the pipe. The local derivative sets how far the valve is open. A wide open valve lets the full error through. A nearly closed valve chokes it down to a trickle. So the backward pass is nothing more than the error signal passing through a sequence of valves, each one scaling it up or down. Let me actually turn the valves, node by node, right to left. First valve going backward is the second activation. Its local derivative is the slope of that squash. Since its input 3.5 was positive, the slope is 1. The valve is fully open, so the error passes through unchanged, still 1.5. Next backward is the add bias node of layer 2. Addition is gentle, it just passes its input along, so its local derivative is 1. The error to the pre-activation stays 1.5. Adding never chokes the flow. Now the second multiply node, And this is where a weights gradient is born. The output was weight 2 times the incoming activation. Its sensitivity to the weight is that activation, 7. So the gradient of the loss with respect to weight 2 is the error, 1.5 times 7. 1.5 times 7 is 10.5. That is a concrete gradient for weight 2. It tells us the loss is quite sensitive to that weight right now, and in which direction to move it. But we still need to push blame further left, toward layer 1. The multiply node also passes error back to its input, scaled by the weight itself. So the error continues leftward as 1.5 times 1/2. 1.5 times 1/2 is 0.75. Notice the signal shrank because weight 2 was less than 1. Weights act as valves too, and a small weight quietly throttles the error on its way back. Now the first activation valve. Its input, the 7 from earlier, was positive, so again the slope is 1 and the valve is open. 0.75 passes through unchanged into the first pre-activation. Through the first add bias node, addition again keeps the valve fully open. The error to layer 1's pre-activation is still 0.75. We are almost back to the weight we care about. And here we arrive at the first multiply node, home of weight 1. Just like before, the gradient of the loss with respect to this weight is the incoming error times the value on the other input line, which was the original input 2. 0.75 times 2 is 1.5. So the gradient of the loss with respect to weight 1 is 1.5. We have our answer, computed entirely by a single backward sweep. Let me step back and look at what that first weight's gradient actually was. It equaled the loss's sensitivity times weight 2 times both activation slopes times the input, a running product of every local slope on the path from the loss back to that weight. This is the deep truth of backpropagation. A single weight's gradient is the product of all the local slopes on the road from the loss back to that weight. Change any one valve and you rescale the whole product. Because it is a product, one number carries enormous power. If any single slope on that path is near 0, the entire product is dragged towards 0. One nearly closed valve chokes the whole pipe, no matter how open the others are. Let me make that concrete. Suppose layer 1's pre-activation had been negative instead of positive. Our squash zeroes out negatives, so its slope there is exactly 0. That valve slams shut. Now trace the product again. Multiply anything by that 0 slope, and weight 1's gradient becomes 0. The error signal simply cannot reach it. As far as learning is concerned, that weight is temporarily deaf. This is not a bug in our toy example. It is the heart of a real problem. When many small slopes multiply across a deep network, gradients shrink exponentially towards 0. That is the vanishing gradient, and early layers stop learning. The same product can also blow up. If slopes are consistently larger than 1, the running product explodes, and gradients become gigantic. That is the exploding gradient, the mirror image of the same multiplicative story. This is exactly why activation functions and their slopes matter so much. A squash whose slope is almost always tiny will strangle learning. This single insight is why the field moved toward activations that keep a healthy slope of 1 over wide ranges. Now notice something we quietly relied on. To compute every backward slope, we needed the values from the forward pass. Weight 2's gradient needed the 7. Weight 1's needed the 2. The forward pass had to happen first, and be remembered. That is the real machine. One forward pass fills every node and stores its value. One backward pass reuses those stored values, turning each valve exactly once. 2 sweeps, and every weight in the network learns its gradient. And here is why it scales. The backward pass reuses the shrinking error signal as a shared running total, so no work is repeated. Computing all the gradients costs about the same as the forward pass itself, not millions of times more. Once we have the gradients, learning is the easy part. Each weight steps a little in the direction that reduces the loss, opposite its gradient. Weight 1, with gradient 1.5, nudges down slightly. Weight 2, with gradient 10.5, nudges down more. Repeat this loop, forward then backward then a small step, thousands of times over many examples, and the loss drifts steadily downhill. That patient loop, powered entirely by these backward-flowing slopes, is how a network actually learns. So the whole mystery collapses into one picture. Values flow forward and light up the graph. Error flows backward through valves, each scaling it by a local slope. A weight's gradient is the product along its path, and one near-zero slope can choke the entire flow. Backpropagation is not magic, and it is not really about brains. It is the chain rule, organized as water flowing backward down pipes, computed once, efficiently, for every weight at the same time. Watch for that choke point and you understand why deep learning is both so powerful and so delicate. If this made it click, subscribe for more visual math.